Well, greetings out there in YouTube land, and welcome to today's video, which will feature a thorough discussion and evaluation of the Eurotubes Biasing Probe. Many viewers have expressed an interest in tube biasing and might be a little intimidated by the methods by which the accurate measurements are derived. Now, this device allows you to simply plug this in to the tube socket and then plug the tube in on top, in effect putting this in series between the amplifier and the tube, and purports to take very, very accurate readings of plate current and plate voltage. Now, of course, what's important is it accurate and reliable? And really, does it make it that much more convenient so that it's worth the price? I'll warn you that the price is slightly over $100 for this, so it's not just some little cheap item you can pick up on a whim. So here's what I propose. Why don't we use this device to bias a single-ended and a double-ended amp, and also do those procedures by hand, the old-fashioned way with the volt-ohm meter, and see how the results compare, see how easy or difficult the procedures are, and try to come up with an understanding of whether or not this device really serves a good purpose and if it's really worth the money. If that sounds interesting to you, then stay tuned, because we're just about to get started. Before we begin the biasing procedure on a single-ended amp, it might be a good idea to review the basic theory behind what we will be doing. And I think it's going to come as a shock that most people bias single-ended amps incorrectly. And why do I say that? Because, let's face it, most of us, and myself included for a long time, will measure the exact resistance of the cathode bias resistor, and then measure the voltage drop across it, and then use Ohm's law to determine what we think is the plate current. But in reality, what we are measuring is the cathode current. Now, some of you may say, well, whatever goes in must come out, so the cathode current should equal the plate current. Well, that would be true except for the presence of something called the screen grid in tetrodes and pentodes, and that's what most output tubes are. Now, when we measured the cathode current using our Ohm's law method, we were measuring the flow of electrons from the cathode, but not all of them reach the plate. And that is because the screen grid will intercept a bunch of the electrons, which will then flow off here out of this wire and be removed from the system. So the flow of electrons that reach the plate is equal to the cathode current minus the screen current. Now, the screen current is usually much lower than the plate current. If your plate current is around 30 milliamps, the screen current may only be 3 or 4 milliamps, so it's around 10%, but still, if you want an accurate bias, you have to take the screen grid into consideration. So I'm going to show you the better method for biasing single-ended amps. We're not going to use Ohm's law down here on the cathode bias resistor, measuring the resistance and the voltage drop across the resistor. We're going to use a different method and directly measure the plate current so that we can get a more accurate bias. Now, the good news is that this method is no more difficult than the cathode resistor method. Also, it's done just about the same way. So here's how we're going to measure it. Instead of using the resistance and voltage drop across the cathode bias resistor and measuring cathode current, we're going to measure the resistance of the primary of the output transformer and then measure the voltage drop across that resistance. Why? Because this will tell us exactly the number of electrons that flow out of the plate and therefore give us the exact plate current measurement. So now you may ask, well, how in heck am I going to figure out the resistance across the primary? Very simple. Look down here at the schematic and you see that in this case pin 2 of the rectifier comes out, comes up, and goes directly to the bottom of that primary winding. We also see that pin 3, which is the plate of the 6V6, is connected to the upper part of that winding. So all we have to do is hook our clips on between pin 3 of the 6V6 and pin 2 of the rectifier and measure the resistance, then turn on the amp, switch our volt-ohmmeter over to DC volts, and measure the voltage drop across that winding. Okay, now I'm going to do that in just a second. We'll demonstrate it so it'll make it very clear. Also, I should add that one of the benefits of this Eurotubes probe is that it purports to directly measure plate current. So let's directly measure it physically here by hand, and then we will use the Eurotubes probe and see if its measurement agrees with our measurement for plate current. Then we will measure the plate voltage between the plate and cathode and calculate plate dissipation. The probe will also measure plate voltage between plate and cathode. We can see then if our plate voltage measurement agrees with the Eurotubes probe and if our plate dissipation calculation agrees from both the manual method and from the probe. Now for the single-ended biasing, our test subject will be this really nice original 1960 Gretsch Model 6151 amp. I also have a proper schematic for it, and as you can see, here's the 6V6, the cathode, the grid, the screen grid, and the plate, just as I drew on my diagram. Let's now pull the back door off this, expose the circuit, and get started. Alright, I've got the little Gretsch amp turned around. I just thought I'd give you a quick peek here at just how beautifully original and nice this is. Little bag of fuses. Other than the 3-wire power cord that I installed and the disconnection of the death cap, it's completely original. And of course I saved that original Gretsch gray cord, which stays in the bottom here for the next owner. Okay, so let's hook up our probes and start measuring the criteria we need to determine our plate dissipation on this 6V6. Alright, let's get started on the manual measurement of plate dissipation in the 6V6 in the Gretsch 6151 amp. And step one will be we're going to check the schematic to see where to put our two clips to determine the resistance and voltage drop across the primary of the output transformer. Now I'm going to warn you that sometimes the schematic is wrong about which of the two filament leads the B+ actually exits from. In the schematic here it says it's from pin 2. It could also be from pin 8, one or the other. Let's look at the rectifier in the 6151 and see which one it is. Alright, here's the rectifier base, here's pin 2, and here's pin 8. Now when I look real closely I only see one filament lead exiting from this pin, but I see two exiting from pin 8. So in this case the schematic was wrong. The B+ through that yellow wire down at the bottom there is exiting from pin 8. So I'm going to put one of my ohmmeter leads on this pin, and fortunately the plate output doesn't vary, so we know we need to connect the other ohm meter lead to pin 3 of the 6V6, which is 1, 2, 3, this one right here. So now I'm going to set down the camera and connect the test leads to this pin and this pin, and we'll measure the resistance of the primary winding of the output transformer. Okay, our ohm meter leads are connected between pin 8 and pin 3, and we see that the resistance of the primary winding of the output transformer is 269, let's say 270 ohms, and I'm going to write that down right here on the diagram. Okay, now we plug the amp into our current limiter. We change our ohm meter to a DC voltmeter, and we turn on the amp and allow the plate current to stabilize, which will take probably 30 or 45 seconds, and then we'll take what we hope is a very accurate reading. Here it goes, it's taken off. Alright, the voltage drop is pretty well stabilized at around 10.79 volts, which I will write down here on the diagram. Then using Ohm's law, just like we would have with the cathode bias resistor, we divide the voltage drop by the primary resistance, and we get a plate current of 39.96 milliamps, which I'm going to round up to 40 milliamps. Next, we need to measure the plate voltage between the plate and cathode, and then we'll have all we need to calculate the plate dissipation of this 6V6. So now I will connect my voltmeter probes between pin 3 and pin 8 of the 6V6, as you see here. Then we'll turn the amp on and wait for the plate voltage to stabilize, and we'll take, we hope, an accurate reading. And it looks like our plate voltage between the plate, pin 3, and the cathode, pin 8, is 269.5. Now, using Ohm's law, just as we would with the cathode bias resistor, we will multiply the plate current in amps, 0.04, times the plate voltage, and end up with a plate dissipation of 10.78 watts. Now let's repeat the procedure with the Eurotubes probe and see how our results agree. Okay, step 1, remove the 6V6 from its socket. Now, in most amps, you could probably do this without even removing the back door. You could just reach in and pull the tube. Step 2, we install the probe socket into the tube socket of the amp. And then step 3, we just install the tube in the probe socket, all of which took probably, a matter of seconds. Also, it should be noted then that the probe is in series between the tube and the socket. Next step, we turn on the amp and allow the 6V6 to warm up fully and for the readings to stabilize, and then we will take those readings from our Eurotubes Biasing Probe. The instructions say to wait about 5 minutes before taking the readings, and I have done that, so we're going to take them. Plate current at 39.5, plate volts at 272. Alright, now that we've done the biasing both ways, let's compare the results. Okay, the plate current we said was 40 milliamps by hand, 39.5 milliamps using the Eurotubes. The plate voltage was 269.5 by hand, and it's 272 with the Eurotubes. The calculated plate dissipation then is 10.78 watts by hand, or 10.74 watts with the Eurotubes probe. I would say that's fairly extraordinary agreement between the two values. And then finally, I prepared a little table here for you. The upper row are the manual readings, the lower row are the Eurotube readings, And as you can see, the agreement is extraordinary, particularly in the most important criteria here of plate dissipation. The results are virtually identical. You know what? Before we go to the double-ended amp, just for the heck of it, why don't we check the bias using the bias resistor method and see if it does come out higher. Remember, this will be measuring cathode current, not plate current, and we can subtract the direct plate current value from the cathode current value and figure out what our screen current is in the 6V6. Okay, let's measure the resistance of the cathode bias resistor. Looks like it's 331.3 ohms, which I will write down. And it appears that the voltage drop across the cathode bias resistor has pretty well stabilized at 13.65 volts. So this voltage drop across this resistance by Ohm's law gives us 41.2 milliamps of current. Now, if we subtract the average plate current that we got by the other two methods, from that we see that the screen current is 1.45 milliamps. So as you can see, if you use the cathode bias resistor method, your estimate of the plate current is going to be high by, what is that, about 1.45 milliamps. Okay, so your plate dissipation calculations will also be high as a result. Well, look what FedEx just dropped off here at the house. 3 good-sized boxes, all from one viewer named David Frassetto, whose generosity is overwhelming. I can't even imagine what just the shipping would cost on these 3 boxes. But anyway, if you're as curious as I am, let's get these open and see what David sent us. Well, this is absolutely astounding. Here is a complete, nice-looking combo amp. I see the name Lessman in there on the side, which is a company that used to make accordions and accordion amplifiers. There is another cabinet here with a nice grill cloth. It may be a speaker cabinet or another combo amp. And then, God only knows, a small kind of compact black box and a whole bunch of NOS tubes. Good grief. Well, I am absolutely astounded by the generosity here, David, and I can't wait to get these things out of the boxes to properly assess them. So I'm going to set down the camera and do that. Okay, first I want to say that everything was just perfectly expertly packed and arrived in really great shape. Obviously not packed by UPS, but by David himself. Let's look at the treasures. A beautiful National Radio Institute tube tester with all the literature. This thing looks mint. Okay, that's the first item. Second is a Lessman Echo amp, which means it, I don't know, must have what, reverb or delay or something of that sort. And then check this out, a Gibson Reverb Echo Maestro Deluxe, which is gonna be a super nice item, a great Gibson handle, nice grill cloth. It's a little musty, it's been in storage, but I bet you it's gonna clean up real nice. Then look at these tubes. We got some Genelex KT61s, a matched pair of 6550s, the tubes for the Maestro, and several other tubes. So I think you got to agree this is a pretty impressive haul. And I think we all owe David a big thanks, because I can see at least 2 really good videos coming out of this. So let me start putting this stuff away and checking it out and planning for future features for each of these. Thanks again, David. Welcome back from that short break. Now it's time to start on the double-ended biasing portion of our video. Our test subject for this will be another Gretsch. This is a 1955 Tweed Model 6155 Electromatic Artist Gretsch amp. but what makes it perfect for our purposes is that it is a double-ended with 6 V6 output tubes in a push-pull arrangement. So let's turn it around, remove the back door and the chassis, and let's get started doing our manual biasing procedure. Okay, I've got the back off here, and as you can see, it's a just super nice original old Gretsch amp. I've featured this in several other videos. Also, it should be noted that if I were simply going to use the bias probe for measurements, I could stop at this point of disassembly and simply pull the tubes and plug in the probe to either socket. But since we're going to do the manual method first, I've got to extract the chassis so that I can gain access to some test points in the circuit. Alright, I removed the chassis from the cabinet. Because this amp has an electrodynamic speaker, I had to be real careful. I can only remove the chassis just so far without stressing the speaker wires. As a little aside, I remember when I got this amp years ago, it had a rat's nest made from mainly from tin foil in here. If you can imagine the short circuits, fortunately I cleaned it all out and rechecked everything before I plugged it in, or I imagine 4th of July would have come early that year. Okay, let's get started then on our biasing procedure by checking out the schematic to see where our test points, our checkpoints are. Alright, first off we see that the amp is cathode biased, but as we discussed in the first part of the video, we do not want to measure cathode current, we want to measure plate current. And in this case, instead of a single winding of the primary of the output transformer, we have 2 half windings. We have this half winding here for this plate and this half winding down here for this plate. However, our procedure will be just the same. It'll just be done twice. Okay, we need to figure out then the resistance of this half winding, and as I see it comes straight through here to pin 4, and then we come back through and up here to pin 3. So it would appear that if I measure the resistance between pins 3 and 4 on each output tube, I will find out the resistance of the half winding here in the primary of the output transformer. Okay, we're ready to measure the resistance of the half winding of the output transformer primary for this tube, and you need to differentiate between them. So this will be the right tube, okay, and that's the left tube. When I write down the results here, I will make sure that I label it right tube. You see I have the test probes here on pin 3 and pin 4, and now let's see what our resistance reading is. And we see that the resistance for that half winding for the right tube is 221.5. And for the left-hand tube, it is 253.6 ohms. And I write both the resistance values down on the schematic for the respective half windings of the output transformer primary. Now with the leads still connected to pins 3 and 4 of the left-hand 6V6, we'll do exactly what we did with the single-ended amp. We'll plug this one in, turn it on, set our meter to DC volts, and then let the circuit come on and have the voltage stabilize. And we see that the voltage drop across that half winding for the left-hand tube is 9.01 volts. And the voltage drop across this output transformer primary winding for the right-hand tube is 8.56. And now with the probes connecting the plate at pin 3 with the cathode at pin 8, we see that the net plate voltage on the 6V6s is 259.3. Using Ohm's law for the left-hand tube, we have this voltage drop, okay, across this resistance, which gives us a plate current of 35.5 milliamps. When we multiply that times the plate voltage of 259.3, we end up with 9.21 plate dissipation on the left-hand tube. On the right-hand tube, we have a voltage drop of 8.56 divided by 221.5 ohms gives us a plate current of 38.65 milliamps multiplied times the plate voltage gives us a plate dissipation of 10.02 watts. Now I've tabulated those values down here on our chart for the manual method. Next we'll do the Eurotubes method and see how they compare with each of the values that we got by our manual method. Okay, because it actually makes things easier, I put the chassis back into the cabinet and installed the Eurotubes probe in between the circuit and the tube as we did with a single-ended amp. Now all we have to do is just plug it into the current limiter, turn it on, and then wait for the values to stabilize. And after a couple of minutes of stabilization, the Eurotubes probe says that our plate current is 35.5 milliamps, plate voltage is 259. And I have written that down right here. Now I've changed the probe over to the right hand 6V6. We'll turn on the amp, let the reading stabilize, and then see what our plate current and plate voltage are in our right 6V6. Well, it seems to have stabilized pretty well at 38.6 milliamps and 261 volts plate voltage. Here is the final tabulation of our double-ended amp biasing experiment with the results from the manual method on top, the Eurotubes method in the second row, and the percent of difference at the bottom. If you compare the results from top to bottom, in each column you'll see that the agreement between the results is almost perfect. In fact, the percentage of difference between any two measurements is less than 1% in every case, and actually 0% in a couple cases. What this says is there is no difference in result. Whether you do it manually or with the Eurotubes probe, you will get the same answer. Well, it looks like we have a new package from a viewer, and Jack is in good sniffing form, so I guess it's time to open it up and see what's inside. Right, Jack? Due to Jack's lack of enthusiasm, I feel confident that this package from a Mr. Jim Robinson must have come from a mouse-free environment. Right, Jackie? Uh-oh, Jack. Look here, what Jim included for you. For you and Casey, some tasty treats. Let's open those up and see how you like them before we look here at all the nice vacuum tubes that Jim sent us. Wow, these yummies smell so good, I think I'll have some. Here you go, Jack. Oh, he wants these. There's some. Casey, come here and get your yummies. Casey, yummies. And there's some yummies for Casey. Always an avid eater, believe me. What do you think, guys? They both say thanks, Jim. Okay, now it's time to open up the vacuum tubes and see what we got. You like those yummies, Casey? Well, it looks like we have a treasure trove here of very useful tubes. 6V6s, 5Y3s, some unusual brands like Channel Master, a Dumont, 12AX7s. Look at this. Original kind of a carton of very desirable tubes. And Jim wrapped each one of them individually, which took a lot of time and effort. And I just want you to know how much we appreciate it, Jim. Jack and Ollie really like their treats, and I really like the tubes. So thanks so much. Now it's time to discuss our findings and how the Eurotubes Bias Probe applies to us as amplifier owners. First, let's discuss the positive aspects. Number one, we've seen that it is absolutely accurate. Okay, it's exactly the same as if you took the amp to a qualified tech and had a manual bias measurement made of your output tube. Second is it's extremely easy to operate, virtually foolproof, and extremely convenient. And you can save a lot of money by doing your own tube biasing at home. And if you're capable, you can, if you find the bias is not correct, remove the chassis and make the proper modifications or replace the output tubes. If you aren't handy, at least then you'll know exactly what's wrong with the amp, and you can either order output tubes or take it to a qualified tech and get the work done. No matter what, you're better off. Okay, if you are qualified to work on the circuit, this will give you a very easy and convenient tool for determining the bias measurements, which are probably the most important measurements that relate to the amplifier circuit. If you are not qualified to work on the circuit, at least then you're informed as to exactly what the situation is, and you can, one, order replacement output tubes yourself and save having to go to a tech to find out that you need them, or second, take it to the tech and be informed at the time, both before you take it to him and after you get it home, when you double check, to know exactly whether or not the problem was addressed and properly repaired. Now let's discuss the negative aspects, and the only one I can see is cost. Okay, the unit cost is shade over $100. Now there's two ways to look at that. If you are not qualified to do the manual biasing procedure on your circuit, then I think it would be a great investment for you. The first time you use it, you'll be saving money, because I know of no techs on earth who are going to do manual bias measurement on your circuit for less than $100. Okay? But there is another alternative. Simply because this thing is really not rocket science, let's take a look at how it works and see if you might not want to build your own. Now what it consists of is a DC ammeter and a DC voltmeter in one package, but the trick is right up here in the probe. That's really where the magic lies. Okay, I think most of us own these two instruments, but this is the thing that we would have to make in order to create our own bias probe unit. Let's take a look at how this is wired. First off, it consists of two pieces. The bottom is just like a tube base with the prongs and the indexing prong here in the middle, and the top is simply a tube socket. Now you can buy all sorts of tube bases like these, or octal plugs on eBay or from electronic supply stores like Antique Electronic Supply. Also, your octal plug will often come with a metal backing like this with a nice grommet, which is a great idea to protect you from being shocked by any exposed metal like where you've soldered onto the pins. Or if all else fails, you can simply break away the glass envelope here from an old 6v6 in this case, and unsolder the wires from the tube pins and then use it as your plug. Now there's something we need to discuss before we move on to the wiring diagram, and it has to do with the way tube sockets and tube plugs are numbered. When we turn the tube socket over and see the pins, which is where we'll be doing our soldering, we locate that indexing notch at the bottom, and we go just to the left. We see that the pins are numbered 1, 2, 3, 4 clockwise. Okay? Now when we look at the plug from the side that we will be doing our soldering, this corresponds to the indexing notch, and we get the notch at the bottom. We see that number 1 is here, 2, 3, 4, and on. So number 1 begins to the right of the indexing notch, and the pins are numbered counterclockwise. Please keep that in mind when we do look at the wiring diagram. Okay, let's take a look at a simple wiring diagram. On the left will be the tube socket that we'll be plugging our 6V6 into. We'll be dealing with the rear of the socket and the pins. I've marked where the indexing notch is with white on both the tube socket and the plug. Remember that the pins on the socket are numbered starting just to the left of the indexing notch, and they're clockwise, 1, 2, 3, 4, etc. And over here on the plug, from the indexing notch, they're numbered counterclockwise, 1, 2, 3, 4, etc. Now, even though there are 8 pins, there are only 6 connections. Pin 1 and pin 6 on both the socket and the plug have no connection. The remaining pins are connected straight across, 7 to 7 for heater A, 2 to 2 for heater B, 8 to 8 for cathode, 5 to 5 for grid, and 4 to 4 for screen. The only exception is that pin 3 on the tube socket does not connect directly to pin 3 on the tube plug. Instead, we will bring wires out of our wiring bundle connecting the 2 units and have them not connected, because we're going to hook our DC ammeter in series with the red wire from pin 3 of the tube socket and the red wire from pin 3 of the tube plug. The only other special wiring is right here from pin 8 of the plug. You will not only have an 8 to 8 connection for your cathode, you'll also run another wire out from pin 8 and bring it up, and it will be one of the 2 leads that you will attach your DC voltmeter to. You'll see all this. I'll demonstrate it in a few minutes, so don't get confused, okay? But just run 2 wires from pin 8. One goes directly over here to the tube socket, and the other will just come out and be loose for us to hook our DC voltmeter to. We'll also hook our DC voltmeter to the lead from the tube plug that comes from the plate. And a couple little side suggestions here. It's almost impossible to duplicate this probe. Okay, you're going to end up with wires running between the tube socket and the plug that you probably can't tuck in right here. And that's really not a problem. When I build mine, I'm going to have like an umbilical cord here between the two that's probably close to 6 inches long. Now here's why that's actually an advantage. When you have a tube plugged in to your this probe, on some head cabinets where the top of the cabinet is fairly low, you might not be able to fit this into the chassis, and you might actually have to pull the chassis out of the cabinet to install the tube and probe. If you have this sort of flexible umbilical cord though, you can plug this end into your amp and then have it come out the back of the cabinet, and you can plug your tube into the socket. The one downside of that is that these pins will be somewhat exposed if you have an umbilical cord like this, and you really need to come up with like a piece of PVC or rubber wrapped around here so that where the wires connect to the pins of the tube socket, there's no chance of you grabbing a hold of this and getting like the plate voltage applied across through your fingers or hand. So be sure that you insulate all the metal parts very, very carefully. Another advantage to making your own probe is this is octal. Okay, this is only for 6V6s, 6L6s, 5881s, and the like. Now what if you have 6BQ5 output tubes, and you want to make a bias probe. Well, then you'll have to hunt down a tube socket, which is no problem, and a plug, which might be a small problem, that suits the 6BQ5 pin pattern. If you can do that, then you can make a 6BQ5 probe, or for that matter, a probe to suit any output tubes that you may be using. With that said, let's go out to the workshop and install the wiring that will connect the tube socket to the tube plug and make our own test probe. Now we're out in the workshop where the probe will actually be constructed. Number 1 pin has no connection, so we go to number 2, and that's going to be our heater B connection. So I run my first wire from the second pin clockwise from the indexing notch over to the second pin counterclockwise from the indexing notch. This is the tube socket. This is the tube plug. Now I will continue and wire 3, 4, 5, 7, and 8 in the same manner that you see in the wiring diagram. I will leave the pin 3 plate wires open so that I can connect my ammeter, and when I get to pin 8 on the plug, I will put in 2 wires, one to connect over to the cathode pin 8 here, and the other to come out for me to connect my DC voltmeter. Also, a little hint to avoid embarrassment: if you're going to use the metal cover like I showed you on the rear of your octal plug, be sure to run the wires through the grommet, okay, when you're wiring, because after you've connected all the wires, you're going to find that you can't slide the metal cover on if the wires are already in place. Trust me, I learned this from experience. Okay, here's the probe that I built. I know you all can probably do a whole lot better, but here is the plug that goes into the amplifier tube socket with the metal cover and the rubber grommet. I covered the wires that are running between the plug and the socket with some of this kind of corrugated material you can buy at auto parts places, and I just thought it gives it flexibility, it covers the wires, it just looks a little more professional. Now at this end, I simply used a lid from an aerosol can that I had. I cut a hole here so that the corrugated wire covering could fit inside, did a little super glue to be sure it stayed there, and this way it insulates me and protects me from the high voltage on the pins of the tube socket that's down inside. Next, I ran those 2 plate wires down here to my little test probe plug-in board. Now, I did this because you don't need exposure to the high voltage. Okay, maybe you can handle it, but if the phone rings while you're doing this and you go answer it and your cat sniffs across 450 volts, or your kid, God forbid, touches it, it's going to ruin your day. Okay, so what I've done is I've used just plain old RCA jacks, and the high voltage is down on the element that's buried deep inside each of these. And I had a spare set of leads, so I just cut off the ends and put on the RCA male jacks, and created a special set of test leads that can work with these plugs. And I've also come up with a way where you only need one multimeter to take both readings, not simultaneously, but I only had one set of probes, so this method just seemed natural. Let me show you how it works. Alright, I've got my tube in position here in the tube socket. I plug this into the amplifier. I turn on the amp. I have my 2 probes plugged into the plate current sockets. I come over here and I turn this to milliamps, and I take my reading. Once it's stabilized and I get a good reading, I shut everything down. Then I jumper the plate current socket so that the current can still flow from pin 3. The B plus will come here through the jumper and go to the tube. The tube will now develop plate current and plate voltage normally. Then I plug my multimeter RCA probes into the plate voltage sockets, change over to DC volts, let it stabilize, and get my plate voltage net between the plate and the cathode. That's the cathode wire, the blue one there, which comes down right here. The plate wire, I just jumpered from this side to this side. Both of them are connected here to the plug that goes into the circuit. Now I kind of went the extra mile here to prepare this readout module here that has no exposed high voltage. And I really think you should do the same. You can come up probably, again, with a better idea than I have. You could use even male and female spade connectors that are insulated, something like that. But you really need to be sure that there's not 450 volts sticking out here somewhere where you can brush your arm on it, or God forbid, someone else or something else brush across it. Well, I guess that's about it for this video. We covered a lot of ground, including the differentiation between cathode current and plate current, a review of how to bias single-ended and double-ended amps, a detailed evaluation of the Eurotubes Biasing Probe, and then a quick presentation on how to create our own biasing probe. I hope you enjoyed it and that you will stay tuned for future videos. I want to give my heartfelt thanks to all my Patreon patrons and PayPal contributors who have kept us on the air and advertising free for another great month. I also want to give my thanks to generous viewers like Joseph Von Kanel, who sent me the Eurotubes bias device as a gift, and which developed into this video. And also to all the generous viewers who have been sending tubes and components, and even some early vintage tube gear. And for those of you who would like to join others in supporting our channel, I will put links in the video description to assist you to do so. And now it's time to get out of this hot workshop and go back to that big car show at the War Eagles Air Museum. I hope you'll join me, and I hope to see you again soon in future videos. Bye for now. Well, talk about wretched excess. Here it is. Look at this thing. Plus it doesn't have wheelie bars. Here's the engine on that noisy black 33 or 34. Just pulling in. Gorgeous. Geez, you need a degree in physics just to read the meters. Selling cars, I'm buying cars. Here's the proud owner. Well, check out this jewel. 34 Ford from Virginia. Nice small rear tires. Good grief. Yeah, we saw this one when it was pulling in. Oh man. Obviously built with gas economy in mind. Yeah, it kind of car sick looking. All the designs on the interior, like an acid flashback. Pretty fierce. Here's something special, a pearlescent old, I don't know what, 41 Chevy or so, two-door sedan with every accessory known to man, the visor, the dice, the wind deflector, the cruiser skirts, the curb feelers, like checked every box in the J.C. Whitney catalog. Okay, and something I don't understand is why that little scallop's aim in the wrong direction, like a fish hook. very unusual. Just to show you, they can't all be show cars. You can have your 40 Ford in a semi-completed state and still show up for the party. Or you can go absolutely nuts and fix up your Pontiac like this, which would take about 4 years, and the gross national product of Venezuela probably, which is, I think, in the negative numbers. Look at this thing.
I was slacking off thinking that...
No, this ain't no... Even though it's got a little power glide in it, still with that...
Gorgeous Pontiac coupe.
300s?
Spectacular car.
272, so...
Beautiful detailing, perfect body.
It's not too bad on the highway.
Well, don't you want to? Do we get to go in the museum?
Good interior. Now for the old-fashioned type of hot rod, the two-door sedan, jacked up in the back with the push bar, got the differential painted to match. I remember these back when I was a kid. This was pretty hot stuff. Look at that exhaust. Perfect to burn your ankle when you get out.
Your brake lines, rubber ones.
I'm not sure. I think it's one. It could be one of the lines.
I would suspect that.
For
All
some
kinds
reason,
of variations in
I hit the brakes
what
and
people
it
like.
wanted to pull it to the right.
Yeah, that means that one there is no.
Well, it's 10:30. The show doesn't really start till 11, but as you can see, there is quite a lineup of cars here. I was really looking forward to this show. I knew it was going to be a good one. I remember the good old days when T-buckets were the rage. I had one about, 30 years ago. About killed myself. And this one is quite an example here. Got a long bed on it, if you can imagine that. I think that's a little odd, kind of different. All it's lacking now is that it's a dump truck bed. That would be exciting. Then look at the, I guess that's the tank under there. No, I don't know. I see things like this, I'm hesitant to find fault for about a split second. But why would you build a really nice T-bucket like this and then tack on a long bed and a hideous steamer trunk gas tank underneath the back? If you can figure that out, leave a comment and explaining it to the rest of us. And then the bus steering, I can tell you right now, mine had it and it's a nightmare. Okay, it's all over the place, especially if it rains a little bit. Okay, so I guess we pretty well trashed this, but a lot of nice work. Well, now I'm going to take out a little time here from getting down with my own bad self to this funk and take a look at the 65 Corvette. This stock is a stone. I remember when I was a kid, I was probably 23 years old. Finally had a job that paid instead of me paying them, and I bought a
test, 1, 2. Hello, everybody. Good morning, everyone. Thanks for coming out today.
65 air-conditioned automatic for $1,500 and drove it
Buenos
home.
dias.
Now it sounds like they're going to start
today.
chatting with us, so
Our inspection, our National
time
Bar
to
Association, the guys
shut
are
down the
here today.
camera.
We want to thank them.
I remember these when I was a kid. Supposed to be great highway cars. They look like a upside-down bathtub or a cockroach. An old Hudson. Supposed to really run well, though. I think that some of them had like multiple carburetors. Somebody really knocked themselves out on this one. It's in beautiful shape. Well, here's a good-looking 34 Ford. Two-door sedan. Tasteful flames. Oh, Betty laughed when that happened, when the window cracked. Jesus. Ribs on the roof. I would think with that swept-back tail, this might be a Victoria. I'm not an expert on sedans and kind of unusual models of Ford.